Yeah, welcome to complex analysis module part 12. Today we will see what are the zeros, singularities. Zeros, singularities and residue is a very important topic in the complex analysis and has have a important role in engineering problems also. So let's start with zeros. What is zeros? Zeros, let fz be a complex function and a point z equal to z naught is called a zero of fz if fz is analytic at z equal to z naught and fz not equal to 0. Means a point becomes zeros of any function fz if fz is analytic at z equal to z naught. What is the meaning of analytic? It is differentiable in some neighborhood of z equal to z naught and obviously the point z equal to z naught. And fz naught value is 0. Means it's a look like the solution of this equation. Z naught is the solution of this equation fz equal to 0. If we take equation fz equal to 0, then this is a solution provided at this point function is analytic. So this is called zeros of fz. Zeros of fz. It can be of first order, second order, or mth order. So let's see the definition of order. If at any point, if at any point fz not equal to f dash z not equal to f double dash z not equal to m minus 1th derivative of fz at z not equal to 0. But mth derivative of fz at z naught is not equal to 0. And important point, fz is analytic at analyticity is required at z equal to z naught, then fz, then z naught is called zeros of order m. Mth derivative is non-zero, but before that all the derivative and the function at this point is equal to 0. It's called zeros of mth order. Let's see m equal to 1. If m equal to 1, it is called zero of first order or simple zero. Some people call it as simple zero. What is the definition for it? Fz is analytic at z equal to z naught. Fz not equal to 0, but first derivative at z naught is not equal to 0. M equal to 1 means first derivative is non-zero. If you take m equal to 2, can you generalize the definition? Yes, you can generalize the definition. Definition will be if m equal to 2, then provided it's called zero of second order for m equal to 1, first order or simple zero, two names are there. Then here fz is analytic at z equal to z naught. Can you tell me what will be the next line? Yes, fz naught, f dash z naught, both are 0, but second derivative of fz at z naught not equal to 0. So this is the definition for second order zeros. Let's see one example based on this definition. First example I'm going to discuss the zeros of fz equal to sine z. So here fz equal to sine z, and we are going to see the zeros here. So for the zeros, we know that sine z is analytic everywhere. Analytic everywhere. You can see my first lecture. Now, if it is analytic everywhere, then what can you conclude here? Can you tell me? Yes, we have to check the points where fz is 0. So what will be the point here? Fz equal to sine z equal to 0. Can you tell me where sine z is 0? Sine at n pi. So z will be n pi. We know that 0 is n pi general value. If you put n equal to 0 plus minus 1, you will get different points at zeros. Let's check the nature of what are the zeros. 0, pi, minus pi, 2 pi, minus 2 pi. All are zeros. All are zeros. This is confirmed. Now the doubt is, what is the order of these zeros? Let's check the order. For order, we check the derivative condition. If first derivative is also 0 as each point, then it will can be of second order. If second derivative is 0 and third derivative is non-zero, then it is order of third derivative. Let's check the derivative. So f dash the derivative of sine z is cos z. If you check at these point 0, pi, minus pi, or we can write general n pi, then cos n pi is equal to minus 1 to the power n. It is never 0 for any n. Therefore, first derivative is not 0. It means n pi is a 0 of order 1. Order 1. It is collection of many points, 0, pi, minus pi, but all are the zeros. These are the solution of this function. Means these are satisfying fz equal to 0 condition. But all these solution of order 1 only, because at each point first derivative of function is non-zero. Therefore, zeros can be many, but order we have to check. But in this case, all the zeros of order 1 only, or simple zeros, you can say like this. Next, very important definition I'm going to discuss. This is called singular point or singularity. So let's check what is singularity. Singularity means the point where function is not defined. A point fz equal to z naught at which the function fz is not defined or not analytic. If it is not defined, then obviously it will not be analytic. It's called singular point of fz. So what is singular point is also called singularity. So singular point is the collection of all points where fz is not defined. So it's a collection of all points where fz is not defined. This is called singular points. For example, if you take fz equal to z over z minus z plus 2z minus 1. Can you tell me at which point this function is not defined? At minus 2 and 1. So what are the singular points? Singular point are minus 2 comma 1, because at these points only function fz is not defined. Let's see the second example. Fz equal to e to the power 1 over z minus 3. At z equal to 3, it is tending to e to the power infinity. It tends to infinity, not defined. So what is the singular point? 3 is the singular point. So singular point is the point where function is not defined. Similarly, fz equal to sine 1 by z, z equal to 0. At this point, function is not defined, or you don't know the proper definition. Singular point can be classified in two categories. Singular points. Singular point. First is isolated singular point. Isolated singular point, and second is non-isolated singular point. Isolated singular point again classified in three cases. Removable singular point, RSP, removable singular point, pole singular point, and essential singular point. So I call it as RSP, PSP, ESP. This singular point is not in our syllabus, but I will see definition obviously. Let's check one by one. First definition is removable singular point. First, let's see the isolated and non-isolated, then we will see the categories. isolated and non-isolated singular point. I am covering in one definition only. This is two classification of singular point. Okay. So the singular point fz equal to z naught is called an isolated singular point of fz if we can find a small real number epsilon greater than 0 such that there is a no other singular point of fz in epsilon neighborhood and object equal to z naught. What is the meaning? Suppose you have a singular point z naught where function is not defined. Suppose function is in this form only. At this point, function is not defined. But and if you take any neighborhood of this and no other point is disturbing inside this open disk, or we say the interior of this circle, and I'm taking very small radius, then this point is called isolated singular point because this is isolated. No other point is in the neighborhood of this point. If you have some other points also in this neighborhood, then this point become non-isolated singular point. If no such radius or epsilon exists, then the singular point z equal to z naught is called non-isolated singular point. So let's see some example based on these two definitions, and we can classify what is the difference between isolated and non-isolated singular points. So first example I'm going to discuss here. Fz equal to z over z plus 2 z minus 1. Can you tell me what are the singular points? Singular points are minus 2 and 1. Now our aim to check which type of these singular points are. So for this we draw the neighborhood of these points. So first is 1. So 1, if we take a small radius, suppose this is a radius, very small radius, and another singular point is minus 2. And if we draw a small radius circle here. So can you tell me, is minus 2 is coming in the neighborhood of this circle? No. So 1 is isolated singular point because it is too far. If we take radius 0.1, if we take radius 0.1, 1 is too far. So this is again a isolated singular point. Okay. For C1 circle, if you draw C1 circle, then what will be the interior point for this? Center is 1 and radius is 0.1 and we are inside the circle only. What is second circle? Center is minus 2 minus plus and radius is 0.1. So inside this circle. So inside the first circle, there is a no existence of minus 2 and inside this circle, there is a no existence of 1. Therefore, these 2 points are called isolated singular point. Similarly, you can draw next example. Both the points are isolated singular point. Suppose if you say, sir, we can take a very close point. Yes, you can think over that. But you can take radius very small always, very, very small. If you take very close, I will take a small radius again. Suppose you take 1.005 and you are claiming that, sir, 1 and 1.05 are very, very close. Okay, take, I am taking zoom it. And I am taking very small radius, taking epsilon like 0.000001. Here I am taking again epsilon as 0.00001. Again, at inside this circle, this point does not exist, and inside this point, inside this circle, this point does not exist. So both are isolated singular points. Then you can think, sir, we can always choose such radius. So there will be no non-isolated singular point. No, this is not correct. Let's take another example. In that example, you will not able to find such small radius which is flexible in these first two examples. Okay, let's take this example. Fz equal to sine tan 1 by z. Fz equal to tan 1 by z. It can be written as sine 1 by z over cos 1 by z. What are the singular point? Where the function is not defined. Singular point is the collection of all z where fz is not defined. So can you tell me where fz is not defined? Where the denominator is 0. So the denominator is cos 1 by z is equal to 0. Where is the cos 0? Cos 0 is pi by 2. So general value, we know that cos theta equal to cos alpha, then theta equal to cos 2n pi plus minus alpha. Remember class 10 plus 1 trigonometry, then 1 by z equal to 2n pi plus minus pi by 2. We can more simplify it and we can find the value of z also. If we take pi common and 2 as LCM, it will become 4n plus minus 1 pi by 2. So z is going to be 2 over 4n plus minus 1 pi and n equal to 0, 1, 2, 3 and so on. We know that. As interesting point is here, as n tending to infinity, z is tending to 0. It's a very interesting point. Take a positive sign. Take positive sign. I'm going to tell you very interesting story here. If you take positive sign and if take n equal to 0, then it will become first singular point is 2 over pi. If n equal to 1, it will become 2 over 5 pi. It will become 2 over 9 pi, 2 over 13 pi. Now, if you take the neighborhood of z equal to z0, okay, now draw these 2 points and it is last point is tending to 0 because as n tending to infinity. Okay, so this is the 0 neighborhood. Okay, 0 neighborhood. Maximum value is 2 over pi and these values are reducing here. Okay, this is like 2 by 13, 2 by 5 pi. This is 2 by 9 pi. This is 2 by 11, 2 by 13 pi, 2 by 15 pi. These values are going to small, 2 pi, 17 pi, and so on. It is tending to 0 actually. So if you take a small neighborhood and you take any radius, suppose you take radius 0.00001, and if someone take n tending to infinity, you will get infinitely many points which are lying inside here. Many points, because it is converging to 0 only as n tending to infinity. So read this. In the neighborhood of z equal to z0 contain many points of fz other than z equal to 0. Other than z equal to 0. It look like 2 over 10 to the power 11 pi. Then this is also very small value tending to 0, but is not exactly 0, but in the neighborhood of z equal to 0. If you take epsilon this and we take this point, then this is the epsilon is greater than this point. So this point will also lie inside the circle only. Therefore, z equal to 0 is a non-isolated singular point because it had some crowd nearby to him. Therefore, this is a non-isolated. If there is a no crowd of any nearby to any point, then point is called isolated singular point. Let's see the classification of isolated singular point. I told you classification isolated singular point having 3 categories. First is removable singular point. Let's see the first case, isolated singular point. I told you it has 3 categories. Removable singular point, second is pole singular point, and third is essential singular point. So let's see removable singular point first. It has 2 definitions. I'm going to discuss with first definition, then second definition. If the function fz is not defined at z equal to z0, then it will become obviously singular point. Then only we can discuss something. Singular point means function is not defined at that point. But limit z tending to z0 fz exists. Function is not defined, but limiting case is existing. Then z equal to z0 is said to be removable singular point. For example, if you take fz equal to sine z by z, and we know that this point is not defined at denominator is 0, so z equal to 0 is a singular point. And if you put f0 is actually sine 0 by 0, so 0 by 0 case. This is not defined, but limit case at z tending to 0, sine z by z equal to 1. So limit is existing here. LHL, RHL both are 1. Therefore, this point is called removable singular point. What is the second definition? Now I will give other definition with the help of Lorentz series. If you remember the Lorentz series, I told you what is the Lorentz series? Fz can be written as, sigma n equal to 0 to infinity an z minus z naught to the power n plus sigma n equal to 1 to infinity bn z minus z naught to the power minus n. If you remember, or some people call it sigma n equal to 0 to infinity an z minus z naught to the power n plus sigma n equal to 1 to infinity bn over z minus z naught to the power n. I told you this part is called analytic part. Analytic part. If you see the lecture of Lorentz, this part is called principal part, and this part has crucial role in the theory of residue and singularity. So let's see what is the meaning of this. If Lorentz series of fz about any singular point z equal to z naught has no principal part, then z equal to z naught is called removable singular point. Let's check. If z equal to sine z, z equal to 0 is singular point. You can observe that at z equal to 0, function is not defined. Now, if you expand about z equal to 0 using Maclaurin series or Taylor series of sine z, then expansion is z minus z cube by factorial 3 plus z to the power 5 by factorial 5 and so on. 1 by z, multiply z inside. All the powers are positive. If all the powers are positive or contain constant term, if n equal to 0, we can write a naught plus a1 z minus z naught to the power 1 plus so on. This is called all the powers are positive or constant term. Then this part is actually analytic part. The part in which powers are negative, if you expand it, it can be written as b1 z minus z naught to the power minus 1 plus b2 z minus z naught to the power minus 2. Then only this is called principal part. But here no principal part, therefore z equal to 0 is called a removable singular point. Okay, pole singular point. Pole singular point. This is the next definition. Pole singular point. And now I'm giving all the definition with the help of only Lorentz series. Pole singularity, a pole singular point. Singular point also called singularity. If the principal part PP, I will say in the shortcut now PP, of Lorentz series expansion of the fz about singular point where function is not defined, z equal to z naught, has finite number of terms. If you see carefully, I told you that the expansion contain infinitely many terms. This is infinity term, this is infinity term. But in the principal part, there are infinity term. But if you suppose you have finite term, then this is called pole of that order. Suppose fz has the form, fz can be written as sigma n equal to 0 to infinity. This is analytic part. This is a meaningless here. Plus sum n equal to 1 to m. There are only m part. Dn over z minus z naught to the power n. The part is finite. Means principal part can be written as b1 over z minus z naught plus b2 over z minus z naught square plus so on bm over z minus z naught to the power m. Then see the maximum power, that is order of pole. So here z equal to z naught is called pole of order m. Pole of order m. Maximum power is m. In particular, if m equal to 1, then it is called simple pole. It is called simple pole. Then you have one term if m equal to 1. Let's see one example. Fz equal to 1 over z minus 3 plus 1 over z minus 2 to the power 5 plus 1 over z minus 7 to the power 9. So this is the principal part actually, because power is negative. If you take in the numerator, here is also negative, here is also negative. Singular points are, can you tell me what are the singular points? 2, 3 and 5, because 2, 3 and 7, because at these point only function is not defined. So 2 is a singular point, and which category? Power is negative, so cannot be removable. It has own principal part, and that is only finite number of term, one term and of order 1, or you can say simple pole. What about, sorry, 2 is order 5 actually. 5. 3 is a singular point. 3 is again a singular point, but it is a simple pole because it has only 1 degree. 7 is again singular point of which order? Pole of order 7. Pole of order 9 actually. The degree is 9. It is pole of order 5. Okay. I'm going to discuss a very important remark. You can remember it. If Fz has simple pole at z equal to z naught of order m, then it's a reciprocal 1 upon Fz has 0 of order m at z equal to z naught and vice versa. It is also useful when m equal to 1. This is a very useful remark for solving the problems. If Fz has simple pole at z equal to z naught, then its reciprocal will have 0 of order m at z equal to z naught. Next definition is essential singular point. If the principal part contain infinitely many terms, then the point become essential singular point. The definition is clear. In the first removable, principal part is 0. In the pole singular point, principal part is finite. Number of terms are finite. Here, principal part has infinite terms. So all the three cases here discussed. If the principal part of Lorentz series of the function fz about singular point z equal to z naught has infinite number of terms, then z equal to z naught is called essential singular point. Let's see one example. Fz equal to e to the power 1 over z minus 2. What is the singular point? Singular point is z equal to 2 because at 2 only function is not defined. Now if you expand it, we know that the expansion of e to the power p, e to the power p can be written as 1 plus t square by factorial 2 and so on. So it will become 1 plus 1 over z minus 2 plus 1 upon factorial 2, 1 upon z minus 2 whole square and so on up to infinity terms, and you can see that all the terms have negative power if you take in the numerator. Therefore, the principal part has infinite number of terms. Therefore, z equal to 2 is a essential singular point here. Sometime the singular point become infinity. Then how you tackle? If singular point is infinity, then how you will check it? So next topic and last topic of this lecture is singularity or singular point at z equal to infinity. If singular point is infinity, so fz equal to z, so infinity is a singular point because at infinity function is not defined. But till we have studied singular points are finite. So we are in finite complex plane only. Then how you tackle the infinity? If infinity is not asked, then never take infinity as a singular point. Because if infinity is not asking, it means you are dealing in infinite complex plane and you are excluding infinity. But in some example or question, if it is particular asking, check the singularity at z equal to infinity, then only you have to apply this trick. Otherwise, there is no need to check singularity at z equal to infinity because we suppose that we are dealing in finite complex plane only. So suppose you are checking singularity at z equal to infinity. This way is very simple. fz singularity at z equal to infinity, then put z equal to 1 over w and check singularity of f of 1 by w, because you have replaced z by 1 by w. And suppose this is a new function f of 1 by w equal to z of w, and previously it was fz and we just replaced z by 1 by w, and you are checking z equal to infinity, then you have to check at w equal to 0 and check the singularity at z equal to w equal to 0. You have to use when asked in the question, otherwise no need to check the singularity at z equal to infinity. It is uh, assumed that we are dealing in finite complex plane only. So in the next part we will see how to classify the singularity when questions are given miscellaneous. And till then you can read this lecture. Okay, thank you.